My name is Lara Al-Hariri, a graduate student at Florida State University, the Chemistry and Biochemistry Department. My small talk today is about nanoscale polyelectrolyte, OLEDs. OLED is a semiconductor device of 100 to 500 nanometer thickness, 200 times thinner than human hair. OLED has advantage over LCD. It has wide angle view, brighter color, large surface area coverage, and it is self-luminescent. No need for backlight as in LCDs. It is thinner and lighter than LCDs, which are the nowadays demands of display market. OLED is composed of an anode, cathode, light emissive layer, a Hall transfer layer, and an electron transfer layer. Under electric field, the holes and the electrons are injected into the emissive layer from the anode and the cathode respectively. Holes and electrons move against each other and recombine to form excitons that release energy. The energy released by the excitons excites the emissive layer, which in its turn releases energy in form of heat and light. There are two kinds of organic light emitting diode depending on the emissive layer and the kind of the material that is used in the emissive layer. It is either polymer or small organic molecule. In depositing both of these emissive layers, there are many problems. The first method of deposition is the vapor deposition method, in which most of the molecules crystallize. The second method is the solution coating method, where we can't control the thickness and the roughness of these emissive layers. Moreover, most of the time there is a mixing between the different layers. In my project, I'm using the polyelectrolyte layer by layer assembly to deposit these layers. In such kind of assemblies, we have a higher control at the molecular level. The thickness and the roughness can be easily controlled. It is an easy, reproducible, non-problematic way of deposition. In such kind of assemblies, we can easily alter the electrical properties of these multi-layer by simply changing the physical parameter. For example, changing the kind of the polyanion that we're using and the salt concentration. Such kind of deposition can be applied to any charged surface, and it is applicable to large areas. This layer by layer assembly is done by depositing the substrate in a polycation solution, then rinsing it in water to get rid of the excess polycation, then in a polyanion solution, rinse it from the excess polyanion, and doing so that on and on using the nanostrata robot. In my project, I'm using PXT, which is a polycation, and which have this good leaving group, the tetrahydrothiophene, that upon heating it is changed from PXT to PPV, which is a light conducting and conducting and light emitting polymer. It is easy to synthesize this polymer in our lab. To differentiate between PXT and PPV, we're using infrared spectroscopy. PXT has two characteristic peaks in the infrared region, the carbon-sulfur stretch at 666 and the CH2 stretch at 2941. PPV also has two peaks, the carbon-hydrogen bend and stretch at 964 and 3024. Now we're using the UV to get an idea about the wavelengths of emission, and to get an idea about the conjugation and the percentage of elimination. This is one of the systems that I'm working on, which is assembling PXT and PSS in multi-layers and heating them at 210 degrees for 10 minutes under vacuum. This is the spectra of the multi-layer before and after heating. As you can see, there is a redshift from 327 nanometer to 342 nanometer, which indicate that elimination and conjugation is taking place. As I mentioned before, that we can alter the electrical properties of this multi-layer by simply changing the concentration of salt. This is an example of PXT PSS multi-layer without salt and with salt. As you can see that the one with salt has more illumination. I would like to acknowledge Professor Joseph Schlenov for his supervision and the Schlenov's group member and Martic for funding.